Welcome everyone. Good evening and welcome to this next distinguished lecture series talk of the Stuttgart ELLIS unit. My name is Andreas Bulling and I'm one of the directors of the unit. The second director excuses himself. He had to see a doctor on short notice and hence he cannot attend today, unfortunately. But I'm very happy to be the host for tonight's talk and to welcome Simo Särkkä from Aalto University. We are very happy to have him here. It will be a very exciting talk. Before we get started, just a few words on his whereabouts and what he's done before. So he is at the moment associate professor at the Aalto University at the Finnish AI Center for AI. He holds a degree in physics and mathematics and a PhD in electrical and communications engineering from Helsinki. Afterwards, he also spent some time in industry, if I'm not mistaken, about 10 years in different positions. Probably the company you know best is Nokia, where he also worked in different positions there. Then again, he joined Aalto University, first as a senior researcher, academy research fellow, and now, most recently, he is associate prof, and as you mentioned before, on the route to becoming full professor, hopefully very soon. And of course, he's also a fellow at the ELLIS laboratory, and that's also one reason why we invited him. And as I said, we're very happy to have you here, and we are very much looking forward to a super exciting talk. I'm very sure. The stage is yours.
Okay, thank you very much, and it's an honor to be talking in this series. And additionally, I could mention that I'm also affiliated with ELLIS unit Helsinki, so we also have that kind of unit existing. So, my topic today is probabilistic differential equation solving as Bayesian filtering and smoothing, and it's related to the topic that we had or you had a month ago, or actually a couple of weeks ago. But anyway, so it's related to the more general concept of probabilistic numerics. So let's start with the introduction. So what is meant by the probabilistic solving or probabilistic differential equation solving in general, and then let's see how you actually solve those differential equations by using Gaussian process regression. But then we will go to see what is something called Bayesian filtering and smoothing, which is related to some fast methods to solve Gaussian process regression problems in the end. And to that topic, we actually get in this fourth section where we discuss the probabilistic ODE solving as an instance of Bayesian filtering and smoothing. And then there's a small discussion on extensions to partial differential equations. And finally, I will conclude the talk. So let's start with the introduction. So what is the actual problem that we are solving? So let's see, just over here. So we are considering this type of ordinary differential equations, or ODEs, which are first order. So we have already converted them. If it's an nth order equation, we have stacked all the derivatives to single vector, which is the x vector, so that we have a first order differential equation where the right hand side is some nonlinear function of the state x and then function of t, and the t is independent variable. And we consider especially initial value problems, so that we have x0 is some given vector x0. Well, technically speaking, we could also consider like other boundary value problems, but let's not go into that. And so what we want to do is that we want to, find an approximate solution to the ODE. So which means that we have some kind of, we get some kind of approximation, so that at a discrete or finite number of points, this solution or this approximation somehow approximates the actual solution at those points. And then those points are defined on some grid of times, t0, t1 until tn, and okay, so I'm denoting this as t. I will have a bit of a confusion of the symbols at some point, so be careful is that when I define them. And then this function, so that we form the approximation so that this function is somehow evaluated like on this grid, maybe just evaluated at those values, or actually in some methods you might also evaluate it in, say, 2 nearby values. But anyway, so that you have a limitation how many times you can evaluate it. And indeed, in some mathematical sense, this approximation solution is also called ODE solver or numerical solver for the ODE. So we now want to form this kind of approximate solution. So how is it classically done? Classically, you basically use a Taylor series expansion. So you somehow approximate something with polynomial, and then you somehow try to minimize the error, so that you don't actually approximate. I have the more about this approximation on the next slide, but anyway, so you locally approximate this as a polynomial, and then the Taylor series expansion actually, or Taylor's theorem tells you how bad the error will be given that approximation. And it's an error quantification based on the worst case error. So what is the maximum error that we can get by our assumptions, which Taylor's theorem tells. It will be some kind of function of the properties of the f on the right hand side. But anyway, it's a worst case error. But so what is the basic idea of probabilistic ODE solvers? So the idea is that instead of using a worst case error bound, we somehow try to approximate the distribution of the errors instead. And then we compute, say, 95 quantile of the actual solution or the true solution, given that we have a certain kind of approximation in use. So that is the difference between classical ODE solvers and probabilistic solvers. So we try to compute some kind of probability distribution describing the uncertainty in the numerical solution. But actually, to be precise, I'm contradicting myself, because probabilistic solvers are also equivalent to certain kind of worst case bounds on certain Sobolev norms. But I guess philosophically we want to have that probabilistic or distribution of the errors estimated. Okay, so if this upper one is just the worst case error, so these are just like some bounds, then probabilistic solvers try to compute some distribution of the errors. So what is the 95% or 1,000 of the distribution in some way. Okay. And as I already revealed, is that classical ODE solvers are related to polynomial approximations, and polynomial approximations are related to Taylor series expansions. So actually, you can see classical ODE solvers as piecewise polynomial approximations to the solution. So for example, the Euler method is in one interpretation based on approximation, so that x at t is approximately equal to the first order Taylor series expansion of x as function of t centered at t0. So we always expand at previous time and then approximate the solution on the next time step by using the first order Taylor expansion. And this time derivative, well, we have the ODE, so it's the time derivative is the right hand side of the equation, so we can actually replace it with f, and it gives this one. And it turns out that actually even the Runge-Kutta methods kind of do polynomial fitting like this. So that how they do it is that they actually evaluate the function at a few points, and then they fit the polynomial there. And then you have a polynomial approximation of the solution in the end. And because it's a polynomial, it is some kind of a Taylor expansion, so it's possible to analyze the worst case error of these methods by using Taylor's theorem. Okay, But so this is a linear function, this is a polynomial, but we have a lot of other approximations in the world as well, don't we? So that okay, so before that, actually have an illustration. Is that the linear approximation? This means that you just draw a straight line between these 2 points, and then a polynomial might be. So this is actually the second order polynomial between the points. But now you could think about other approximations also instead of polynomials. And indeed, one way, or not one way, but machine learning and statistics have a lot of ways to go beyond polynomial regression models. And one way to think about this, like a neural networks, they are indeed flexible, but you need to use some kind of gradient descent to actually kind of find the optimum. So it works well for applications where you actually have some kind of noisy training data, but to make a quick, exact, or quick closed form fit, actually Gaussian processes are better for. So Gaussian process is another way. So they are actually fast to fit to a small amount of data, provided that you can fix the hyperparameters, and they also provide the error bounds that we are after. And indeed, what the probabilistic ODE solvers do is that they replace that polynomial approximation used in classical solvers by using a Gaussian process. And then by using the Gaussian process solution, we actually have the error bounds available. Of course, then everything else is about details, how you implement that. But okay, so let's see how you actually do it. So how do you do probabilistic ODE solving using Gaussian process regression? So first of all, let's fix the notation and also the formalism. So what Gaussian process regression considers is that we have some unknown function. So it's g of x, like y is equal to g of x. And now we need to be careful because my ODE solution was x, but let's forget about this. So this is just a local variable here, this x. So y is equal to g of x, and this g function is unknown, but instead we are able to get some training samples which are pairs of x's and y's. So xj, yj, where j goes from 1 to capital N. And then we want to predict the value of this function at some certain x star, which would be some kind of like a value between the opposite points or outside, either interpolation or extrapolation. But before doing that, let's fix our notation or change our notation a bit, because x was reserved to our ODE solution. So let's instead, because we actually have a function of time, because that's what the ODE solution is. So let's replace this x input as with t. So we are actually trying to approximate y is equal to g of t. And then we observe the pairs tj and yj. And indeed, the classic way to do, for example, polynomial regression, how it works that you postulate the right-hand side g of t to be, say, linear function or polynomial. And then if you want to fit it to some data, you would just estimate the parameters by doing least squares estimation or Bayesian estimation of the parameters, parameter vector theta. But in Gaussian process regression, what you do is that you instead assume that this g of t is a priori a sample from a Gaussian process with certain covariance function. So for example, the covariance between function values of t and t prime could be assumed to be like a constant times e power 2 minus the difference of the time squared. So this is actually just the absolute value. These are not vectors. It just tells that the correlation between nearby values is bigger than correlation of values which are far away from each other in terms of the inputs. And this is the classic covariance function, which is almost always used in machine learning applications of Gaussian processes. The other one being the mattern, which is the one which we are actually going to use in this lecture. So how you would derive Gaussian post-regression from this? Okay, so first assume that we have fixed these length scale parameters and the overall scale parameter here. So the covariance function is fixed. Then if we denote the observed points as vector y, like this, and the test point will be y star, like this, then what the Gaussian process assumption actually tells is that the joint distribution of all these y's and also y star is a Gaussian. And we can, well, it's actually, we need to assume zero mean, a priori zero mean in addition to the covariance function. But what this covariance function tells is that if we have values of g, we know the joint covariance because it's just this the covariance function evaluated at those time points, because that's the definition of the covariance function. So we actually know that the joint distribution of these will have a zero mean, and then covariance given by this kind of a known expression, where we just evaluate this covariance function at the like known input points or training set points, and then also at the test set points. But then, okay, so we actually don't know y star. And these are defined here. And then, okay, so if you don't know y star, then the Bayesian way to go is that we compute the posterior distribution of y star. And so this is a joint Gaussian thing. So we compute the posterior distribution of y star given y vector here, which we have observed. And then it turns out that the conditional mean of y star given the observed values will be like this, and then the conditional variance will be like this. So this is the Gaussian process regression. So that we can actually this is a form of interpolation or extrapolation of y star from the observed values y, which uses the information about the covariance function, and this is the uncertainty related to the predicted value. And indeed, these equations are going to be used for interpolating or extrapolating this test function value, which we don't know at any given test point input or test point of time. And then just to see how you can handle the measurement noise. So in practice, the measurements have some kind of a, say, Gaussian noise. So yn is equal to g of tn. So tn is the observed point, and then Gaussian noise with zero mean and some variance. And then we want to somehow estimate the value of the clean function, so noise-free function at t star. But then we can almost in a similar way do that. We know that the joint distribution of these noisy values and the noise-free values looks like this. So the mean is still zero, but then we will have something which depends on the covariance function, but then we will have an additional term which depends on the variance of the noise here. But still, it's almost the same as before, so we just have this measurement noise term appearing. We can compute the conditional mean and the variance like this. So even with additive noise in the measurements, we can compute the closed form expected value given the observations for g star, t star, and then the same, and the variance for the same quantity. So these are now more typical Gaussian process regression equations, which also take that noise into account. These are scalar special cases, but I could easily just stack vector g here, and I would have a vector of values here and so on. So it kind of directly generalizes to vector case as well. And so what this looks like, so first we haven't observed anything, so we just have a prior. So this green is the kind of the quantile. So I think it's 95%. So the 95% of the values of the GP should be between this like a upper limit of green and lower limit. But then we can condition that into that point. So what happens? Now we condition that, so that conditionally that the value of the function was this plus a measurement noise. Then we know that, okay, so we can compute that, okay, most likely the correct value for the function value at this observed point is somewhere here. And then the uncertainty just increases when we go away from the observed point. And then we can condition on the next one, and the next one. So we get the expected value and the quantiles of the process, or the Gaussian process, like this. Okay, then to get prepared with that probabilistic ODE solver, we actually need to be able to evaluate or observe the derivative of the Gaussian process regression. But it actually turns out that even if I would have the derivative here, okay, so I actually have it here. So it turns out that if we know the covariance function of G, so we know that G is a Gaussian process with certain covariance function. It turns out that the covariance function of the derivative is just basically a derivative of the covariance function. So we can compute the covariance function of the derivative as well. And then we can do the same trick which we had, is that we stack the observed values of the derivative to a vector with that non-derivative values, and we can magically actually compute the joint covariance of those values, and then we condition the value of G on the derivatives of the G. So even with derivative observations, we can actually write down the closed form solution for the Gaussian process. So it looks like this, unless I missed the term. It should be roughly right. So we just the differentiate. So for example, this k is the e power 2 minus difference of t squared. So we can certainly easily compute this. So this t squared just comes out and becomes a linear term in the front. And then, well, we can imagine what the derivative looks like in the squared exponential covariance function case, which is the example which I had. So these are quite simple expressions. And then, so how do you solve an ODE using GP regression? So that what we have is that we say that this is a 1D case. So what it says is that when we have function x of t, so this says that the time derivative of x of t needs to be like f evaluated at x of t. So it's actually like a relationship between the derivative and the actual value of the process or the solution. So how we can now do is that we use a GP regressor, so that well, we have a GP regressor for g of t, and then we use this Gaussian process to approximate x of t, so that we say that this solution is approximately g of t. But now what this actually tells, it tells that the time derivative of the Gaussian process needs to be equal to f evaluated at the Gaussian process. So it actually tells us that our Gaussian process must satisfy this equation. And because we are interested in our numerical solver, which we define to be just a approximately solution to the ODE at a discrete number of points. So what we actually want to say is that so the Gaussian process satisfies that, so the time derivative of the Gaussian process minus f evaluated at the Gaussian process is equal to 0 at these points Tn. But now this actually defines a nonlinear likelihood, and we can actually condition on this to be true. So we know how to compute the covariance function of the derivative, and we know the covariance function of g, and then there are a bit of details, but we can actually write down the conditional distribution of the Gaussian process given that this condition is true. at least we can imagine that we can approximate that distribution. And indeed, this conditioning of the Gaussian process on this is exactly how the probabilistic ODE solvers work when you implement them by using those Gaussian process regression equations. So it is so that we condition on these, but then we can also compute at any time the not only the mean prediction but also the variance of the prediction. So we actually get the quantiles of the solution at any point of time that we wish. Okay, but how does this Bayesian filtering and smoothing then come to play? So first, well, we need to be careful with the notation because my notation is going to overlap. I'm going to use X again. That's because the probabilistic state-based models are usually formulated in terms of X. And so you need to forget what X meant before for a second because this is going to be slightly different. But so what state space methods and Bayesian filters and smoothers consider is that we have some kind of Markovian, vector Markovian model. So X is the state of the vector process. So like a 10-dimensional real valued vector, for example. And then we have a transition density for that, like a time stepping. K is the time step, so it sums from K to K plus 1 and K plus 2 and so on. So this is the Markovian transition density for that process. And then we have some kind of measurement Y, and we know the likelihood model for the measurement. And what we have is that realization of the model is that we have a X, and then we get observations at its time point. And now the problem that we are trying to solve with Bayesian filters and smoothers is that we do get these observations, Y1, Y2, Y3, Y4, which by the way are vectors of measurements as well, but we don't know X's. And we want to estimate this sequence of X's from sequences of Y's. So this is a Markov model which has hidden state, so this could be called hidden Markov model. But just to clarify, so that our X is not restricted to be a discrete valued, but it's a real valued in general. But anyway, so this is the probabilistic state-based model. And then one simple example is, for example, Gaussian random walk, which, by the way, is a Gaussian process. So that we have some like a next X with the scalar is equal to previous X plus a Gaussian noise, and then the observations are just this X plus a Gaussian noise. So that we have the transition density looks to Gaussian, and likelihood that the measurement is of Gaussian form as well. And so this is actually an illustration of the Gaussian random walk. Okay, but more generally, very typical models. So we have something called Gauss-Markov models, which we have a vector, we have a linear part here, and then this is a vector of Gaussian noises actually. So the transition is Gaussian, a linear Gaussian, and it's Markovian, so it's Gauss-Markov. And then the observations are like a not only conditional Gaussian, but a linear function of the state plus a Gaussian noise. So this is a generic linear Gaussian state space model, also called linear Gaussian Gauss-Markov model. And well, if you look at this carefully, so X is a Gaussian process and Y is a Gaussian process as well. But let's not go into that. But then we could have a typically Gaussian driven nonlinear model, so we could have some nonlinear function of the state and the noise, even when the noise Q and the noise R, they are Gaussian. So this kind of system then defines a non-Gaussian process. Then the same filtering and smoothing formula also works for like a continuous discrete model. So so the difference is actually so that this dynamics can be continuous as well. So this is something called the stochastic differential equation, when these are stochastic difference equations. And then it seems that I have a generalization of the likelihood model already as well. So of course, this one and this one is a special case of this type of models. So we just say that the conditional distribution of y is something given. Okay. And so in principle, well, these define Bayesian models. That's fine. So we could just take our Bayesian toolbox and compute the posterior distribution of time series of x's given a time series of y's, which would be a valid solution to the problem. The problem is that there's a curse of computational complexity, if I could say, is that what we actually get is that we get more and more measurements all the time, because we will have an ODE and we go forward there. And also the state estimation problems also consider the case that we have an increased number of measurements. And with this kind of solution, we have a problem that we need to kind of compute the whole solution all over again, where we get even one more measurement. And then this whole solution actually scales as t power to 3. So when you think hard, you notice that this solution is going to be quite inefficient. Well, it's not tractable when, like, you cannot have a sequential process which scales more than linearly in the number of time series members, because the computational complexity will like hit the top at some point. Okay, but anyway, it's not a good idea to use this batch solution because of the scaling. So instead, we use certain tricks, the Markovian trick, to compute certain kinds of marginals. And they are called filtering distribution, which is it's a distribution of x at time k, given the observation only that time. So it's kind of causal estimate, or like a causal estimate of the state. Then we have the prediction distributions, which are kind of causal estimate and then a couple of steps forward. And then we have the smoothing distributions, which are actually the marginals of this joint distribution. And it turns out that these distributions can be computed in OT time versus OT to the power 3. So OT time by using that filtering and smoothing theory. That's the whole point of the whole filtering and smoothing theory, that can be done very fast. As a side note, so there's also certain parallelization methods where you can even do that in log t time in certain parallelisms. But okay, but the sequential ones are OT. And well, this is a visualization how you do prediction, filtering, and smoothing. So where the measurements are conditioned on. But let's go forward. So what that Bayesian filter actually does. So it is a Bayesian solution to the problem, which just happens to look like this. So that we have so it actually computes this filtering distributions, which are xk conditioned on the measurements up to k, where this k is somewhere in the middle of the interval that we're considering. And what we assume that we know the prior distribution, the state space model, and the measurement sequence. And then what the filter actually is, so it's a recursion or iteration rule to get from the filtering distribution at time k-1 to filtering distribution at time k. And that is called the Bayesian filter. So what it looks like is that, well, we start from certain initial distribution, which is the prior of the x0. And then we have a prediction step, which is the Chapman-Kolmogorov curve equation for Markov processes, and then update step, which is actually the Bayes rule. And then, okay, so here we have the normalization constant. So the solution happens to have a sequential form like this. And this is computing the marginals or filtering distribution type of marginals using linear computational complexity, the number of measurements. Okay, this is the visualization of what it looks like. So there's a prediction step and update step, which can be seen as we use the dynamics and then Bayes rule, and then that results in the posteriori distribution. And the classical filtering algorithms, so there's something called Kalman filter, which is the general solution for any linear Gaussian state space model. And actually, as I mentioned, is that linear Gaussian state space models define Gaussian processes. So it's actually the solutions to any Gaussian process type of state estimation problem, which is actually connected to the Gaussian processes in the sense of machine learning, as we see next. And then extended Kalman filters. So if you happen to have a nonlinear measurement model or nonlinear dynamic model, then you can use extended Kalman filters, which are based on Taylor series expansion of the nonlinearities. Then you have something called unscented Kalman filters, which approximate the moments in a certain way. Then Gauss-Hermite, Kuiper Kalman filters, which again approximate the moments by using certain kind of numerical integration. Then we have particle filters, which use Monte Carlo. Grid. Okay, so it's just grid approximation. Or the mixture Gaussians can be used for approximating. And then we have the smoothing problem. So which is actually the one which we are interested here. Well, so the filtering problem will correspond to our explicit solvers for ODEs, where this smoothing problem will be the implicit solution. Okay, I really revealed my cards already, but okay, so let's see. So that we have this probabilistic state space model, and then how the smoothing solution works is that we assume that these filtering distributions have been computed already. So we have done that forward pass corresponding to the filtering distributions, and then we end up having recursive equation for computing these smoothing distributions in a backward pass. And so it's a backward pass because there's a boundary condition in the end, because it's smoothing coincides with the filtering distribution. But anyway, what happens is that we will have a definite backward iteration or recursion to compute the smoothing distribution with like the same amount of complexity as the number of time steps. So there's a forward pass which computes the marginals of the filtering distribution by using OT steps, but T is the number of observational time points actually here, and then OT backward pass which computes all the marginals of the full posterior distribution of the x's, and that's the Bayesian smoother. And then the linear Gaussian solution is called, well, you could call it Kalman smoother, but because Kalman didn't really come up with that, I guess it's more by Rauchtung, Schriebel. Maybe they are not the right names either, but anyway, those are the names which are connected to the closed form solution, to that backward pass for the linear Gaussian models. Then you can also borrow or use the same kind of approximations for the nonlinear case as for filtering. So you have a Taylor series based extended, sigma point based unscented, or more general sigma points based unscented Rauchtung-Schriebel smoothers. And then you can use numerical integration, so you get Gaussian smoothers. But then I forgot to mention that it's also possible to implement a filter where you kind of iterate at the update step. But then it's actually more sensible to use iterated smoothers. So that after doing like a one forward and backward pass, you can actually improve the approximation by iterating a couple of times. So you basically really linearize at that previous approximation. And what you get is that you get iterated extended Kalman smoothers or extended RTS smoothers, and then something called iterated posterior linearization smoothers, which are, by the way, our contribution. But anyway, we have some work in this area. But iterated extended Kalman smoother is a classical Taylor series based method, and it's possible to show that it actually converges to the maximum a posteriori estimate of the trajectory, because it is basically a clever implementation of the Gauss-Newton optimization method when applied to the nonlinear state space model. And then particle smoothing is another solution. Probabilistic particle smoother is a kind of a mixed Gaussian solution. Okay, so how do you then do probabilistic ODE solving using Bayesian filtering and smoothing? So we know already that Gaussian process regression with the nonlinear measurement model kind of corresponds to that ODE solver, but it has a bit of problem. So that well, it actually has the same problem as the filter was trying to solve, is that it has cubic computational complexity in the number of measurements. And now you need to be careful is that, well, our measurement it was t in the previous slides. Here it's n, but it's kind of the same thing. I will just clarify that the number of time steps in this time series case is the number of measurements. You can think that n and t are capital N and capital N are the same thing. And anyway, so where this cubic complexity comes from, it comes from this because the linear solution with n observations in general scales cubically in the number of measurements, because there's a kind of inversion of n times n matrix. Of course, you don't really need to invert it, but you need to compute, say, Cholesky factorization, which is still n power 3. So whatever you do, this is n power 3, unless you can somehow use some sparseness properties or reduced rank properties or some other things. Well, you can use that. So you get sparse Gaussian processes or reduced rank Gaussian processes. And then if you happen to have a Markovian model, at least I could consider that maybe there's an optimization for it. Yes, actually there is. That's called state space. So Kalman filter is a very good optimization for actually computing this, or actually the smoother. But back to the point. So we could somehow like put these equations into the GP-based ODE solver. So first of all, if you try to approximate the whole trajectory with the GP, so we will have a huge number of observations, and this will scale quite badly. So no, but then we could also do like a local approximation as the Euler does. Yes, that could be done, but that loses some uncertainty information. And so our conclusion from this slide is that, okay, so we don't want to give up trying to use like a global GP-based approximation to the ODE solver, but instead we keep on going, but just make sure that this is going to be computationally tractable. And as I mentioned, that we could use sparse or reduced rank or other approximations to cope with this complexity. But then another way is indeed to use state space methods. And what they do is that they notice that, okay, so linear Gaussian state space models they are Gaussian processes. And then given a linear Gaussian state space, we can use the Kalman filter and RDS smoother for very fast computation. And okay, so let's say that we have any Gaussian process. Maybe we can convert that back to state space model and then use the Kalman filters and smoothers. And yes, so we can actually do that in certain special cases. But that special case happens to be exactly the one which we need in this ODE solving case. So let's see. So first of all, we have different kinds of representation of Gaussian processes. So in machine learning, you typically see like a covariance function representation. So we have a mean and then covariance function. But then if you compute the Fourier transform of the covariance function, you get the spectral density. So an equivalent thing to say is that, okay, so the spectrum of the Gaussian processes, of the random processes, is something like this. So this is basically the variance of the certain spectral band, infinitesimally small spectral band of the Gaussian processes. So it's equivalent to saying that that spectral density of the spectrum is of this form. But then there's yet another form that we can also draw some function from the process, which they look like this. So they are sample, like a random sample from the process. And there exists also now the pathwise representation. So this is a pathwise representation. Maybe you remember from quantum mechanics that there's a path integral formulation and Schrödinger equation and then Heisenberg. They are kind of a similar thing, different kinds of representations of Gaussian processes. Okay, but what the path representation looks like is this one. So path representations of Gaussian processes are actually linear stochastic differential equations which are driven by white noise. So for example, this particular example is something called Ørsted-Uhlenbeck process, which in path representation is a solution to differential equations like this. So time derivative of g is equal to minus constant lambda times g plus a white Gaussian noise. And we can actually, it's relatively easy to actually compute the covariance function. So you can take the Fourier, let's see, the solution is, you take the Fourier transform of this, and then you compute the absolute value squared of the Fourier transform, you will actually get the spectral density, which looks like this. So and then if you compute the Fourier transform or inverse Fourier transform of this S, you will get this kind of covariance function. So that there's a direct link between the path representation, covariance function, and the spectral density representation of this process. And there's one catch, is that, well, like the covariance function always exists. So we can, well, not always, but provided that it's a positive definite function, it's fine. So we can kind of write it down. And then we can also compute the spectral density by computing the Fourier transform of the covariance function. That's fine. But then when does there exist this kind of a differential equation? It does not always exist. It turns out that because the time derivative in the spectral domain is a multiplication with omega. So it turns out that this differential equation and spectral density representation equivalence only exist if this S is a rational function. So if and only if S is a rational function, then there exists a corresponding differential equation or pathwise representation of the Gaussian process. So it's related to the Markovianity, so that if this S is a rational function of finite order, then it's a Markovian process of finite order. But luckily, there exist interesting processes which actually have a rational covariance function. For example, so this is the Ørsted-Uhlenbeck, but then also the whole Mattern class with half integer order parameters actually has this form. Okay, but then what we get from this theory is that if you have a Gaussian process regression problem like this, then it turns out that we can actually convert that into equivalent state-based representation. So this GP prior here, so we can write down the corresponding stochastic differential equation. And now you need to notice that actually, like my differential equation have had X inside them, and also the state estimation problem had X. But now we, because our Gaussian process was denoted by G of T, it will be a differential equation for G. And it's actually a vector of G, which is G and then a couple of derivatives. But anyway, so we can convert this problem into a linear state space model of this kind of form, where this H actually is a matrix which kind of picks the right components from this vector G. And then by the results for stochastic differential equations, we know that we can actually equivalently discretize this linear system into a into this kind of form. And now, if we compare to our Bayesian filtering section, so this is actually a linear Gaussian state space model in a different notation. So it turns out that the Kalman filter is the exact filter for this linear Gaussian state space model, and the RDS smoother is the exact smoother for this state space model, which means that we can actually compute the posteriori distribution of G at any given time t by using the Kalman filter and smoother. And it's going to scale linearly in the number of measurements because it's a Kalman filter and smoother. And so this is the whole story of state space Gaussian process regression, is that we have a Gaussian process regression which depends on time like variable. Then we can convert that into a continuous discrete state space model. And then we can convert that into a discrete time state space model. And then we can solve it with a Kalman filter and smoother. But now we can use the same concept also for the ODE solutions. But okay, so I have a nice animation before that. So you might remember how I had the Gaussian process regression solution, which just we had the green thing and then it was conditioned on each of the points. And now what the Kalman filter does and the smoother is that there's a forward pass. So this is a Kalman filter solution going forward. So this is not yet the full solution. But then what the smoother does, it computes kind of backward quantities like this. And then now this solution is exactly the same as the Gaussian process solution after conditioning on all the observations. But it's just computed in a different way. And it takes just O(n) or OT instead of n to the power 3 or t to the power 3. And so then we have the problem of derivative observations, which we know how to solve with Gaussian process regression. And actually, it turns out that it's even easier with state space models. Because typically when you actually form that state space representation, actually you have to put the time derivative of G into one of the vector components. It's a longer story why, but anyway, so that's how you actually form the state space representation, is that you augment derivatives. So it turns out that the derivative observation case is that, well, you have the same dynamics as before, but you just replace the measurement model. So you replace this matrix. This was H before, but now it's C. Just to illustrate that, if you originally had, this is the typical H matrix, so that this just picks the first component of G, then the corresponding derivative observation is just another kind of matrix. And this also generalizes the multivariate case. Or not multivariate, but high order case. So anyway, so if we know H, it's very easy to form C as well. So we know how to handle derivative observations. So we just replace the measurement model with another linear measurement model. And now, if we take a look at so this dynamic model is equivalent to put in a GP prior. And then the measurement model, well, actually, we don't have a measurement model in the ODE case. But instead, what we have is that we measure that, okay, so the derivative, that the time derivative is equal to f evaluated at the process or the solution value itself. But if our like a prior was this G vector, then we can evaluate the derivative of G by, well, multiplying that with C. So the time derivative of G should be this one, or the approximate time derivative of X. And then we can say that if you subtract f evaluated at the, well, this is the actual value of Gaussian process, then this should be 0. So this is equivalent to this GP being a solution to this differential equation at this point Tn. And actually our solution is that, okay, so we condition our state space dynamic model on these things. It is kind of solvable, so at least I know how to solve that constraint estimation problem, but it's actually the current formulations in papers. So we can also interpret this as a nonlinear measurement model. So if we write that, okay, so let's say that h of g vector is equal to the difference of these. And then we say that, okay, so let's pretend that we have a small measurement noise anyway. Then we can write this condition or boundary condition down as so that we have a measurement z is equal to h of g plus a noise. And then what we do is that, okay, so we let this noise variance approach 0, so it kind of gets well, we get rid of the whole noise, and then like these observations are actually formally going to be each equal to z is equal to 0. So we can do filtering so that we have 0 observations of that difference what we have here. So that we observe at its time t and that the solution to the ODE is satisfied. And it turns out that we can write that down as a filter, so that we run a filter and smoother on this state space model so that we always observe zeros. And this is just a nonlinear filtering and smoothing problem where we just like pseudo observe zeros. And this provides a solution to the GP regression problem related to the ODE solving. So this is actually the probabilistic ODE solver. So we solve this state space model by using an approximated nonlinear filtering and smoothing solution method. So we can use any nonlinear Bayesian filtering as a probabilistic solver. Okay, so the filter will be a causal solution. So like what is the best estimate of the, like say Gn, given that we have had observations from the like up to that time point. So we have observed just to the left in time. And that's exactly the filtering solution corresponding to this model. So the filter gives the like explicit ODE solver solution in a classic way to this problem. And for example, we can use extended Kalman filter, unshaded Kalman filter, particle filter. Okay, with particle filter we get some trouble from the like vanishing measurement noise, but provided that we can get rid of that problem, we can actually use it. But then we could also compute, so we have all the derivative observations or the like boundary observations, and then we compute the conditional distribution of the whole state trajectory given those. So we get something called iterated extended Kalman smoother, or that's one way to approximate the whole trajectory approximation solution. And indeed, it turns out that this corresponds to a form of a global implicit probabilistic ODE solver, which is indeed one which we considered in a paper a couple of years ago. Okay, but so this is the method. So you of course need to put in some details. Is that you formulate the GP problem in state space form, and then you form the pseudo measurement model where you have a vanishing measurement noise, and then you apply either say extended Kalman filter or extended Kalman filter or some other method to that problem, and that gives you the ODE solution. And this is an example of solution to this kind of logistic equation. So we get not only the solution, but also the quantiles of the solution. So this is the solution itself. So the uncertainty increases because we have kind of, well, the further we go, the less we know about the solution. And then this is the derivative. And we get observations of the derivative in some sense always at its time step. So it doesn't, or the uncertainty doesn't increase without a bound. It increases a bit, but anyway, we get a bit back always when we observe. And so extension, so brief discussion how you would extend that to partial differential equations. So we could think about Cauchy type of PDEs, which means that it's a PDE with the first order time derivative and then initial conditions. For example, like a Burger's equation, maybe this would be a notation that you could use for it. So u of, so this t is the time derivative and x is the x derivative. And now, okay, in PDE literature, you use x for the spatial variable. So you need to be careful with the notation. And but at least this is the one which we have been using to test these methods. So the approach is that, well, when you have a PDE of this form, so you can space discretize, which basically converts the partial differential equation into very high dimensional ODE. And so this is called method of lines, I guess. And that's the whole story. So you just discretize the PDE and then you use the ODE toppers. You can be a bit clever in the choosing the prior, so you can use a spatial temporal prior for the PDE solution, which can be used to improve the estimates. But anyway, so it's very similar solution in structure anyway. So possible methods, so you can use finite difference methods, Ritz-Galerkin, finite elements, and so on. And it becomes a finite dimensional state estimation problem, so you can use still the same kind of methods. Of course, you need to be able to scale with the dimension, but in principle, it's straightforward. And then in PDE case, you also have some boundary condition things which actually complicate things, but the same principle still applies. Okay, but let's not go into that detail here. So this is an example of Burger's equation. So we can use finite differences to convert this into a finite dimensional ODE system, actually. And then we can use a prior like this. And then we get not only the solution, but also the variance field for the solution, which is the benefit of the probabilistic solvers. And the point of the Bayesian filter and smoother is that you get much faster computations than using a plain GP solution by using that classic equation. So as a conclusion, so we have been discussing probabilistic differential equation solvers, which aim to provide probabilistic bounds for ODE solutions instead of those worst case bounds. And the basic idea is to replace the polynomial approximations used in the classical ODE solvers by a Gaussian process regressor, which provides the error bounds in terms of distributions. And then it turns out that this GP-based ODE solvers can be reformulated as Bayesian filtering and smoothing problems, which means that we can solve them by using, well, approximate Bayesian filters and smoothers like extended Kalman filters, uncertainty Kalman filters. And then especially the iterated extended Kalman smoother is an interesting one, which corresponds to an implicit solution. And then, okay, so we discussed a bit about the PDE extensions, and but not too much. And here would be a couple of references. So there's a book by Philip and others. Then there's a PDE paper. Then about the state space methods we discussed in our book on the SDEs. And then advertisement. So we will have a second edition of Bayesian filtering and smoothing book coming this year. I'm right now spending my free time in copy editing it. And so Lennart is the second author also there now. And then the EKF and EKS papers are the last two here. Okay, but so thank you. I think this was all from me.